Hi, my name is Ryan Lynch. I'm a systems engineer with Analytical Graphics, and today I'm going to demonstrate a brand new free set of rendezvous proximity operation sequences that you can use inside of Astrogator to design and execute really complex rendezvous and proximity missions without having to be an expert. So we're going to be doing that by replicating the SpaceX Crew launch that happened back in May. And we're going to take a look at kind of a notional example using those RPO sequences to, again, kind of simulate that launch back in May. Okay, so looking at the scenario here, we've got two kind of models happening here, or reference missions. One of them is the Falcon 9 launch that's actually getting the Dragon capsule into orbit. And then the second is the Dragon capsule conducting a series of maneuvers to, again, rendezvous with the International Space Station, and then finally execute a series of maneuvers to capture or dock onto the International Space Station. Okay, so I'm going to just animate here. You can see the Falcon 9 stages 1 and 2 launch here, and kind of, right in line with the International Space Station here. And then the Dragon is deployed from stage 2 there. And, just briefly, this first bit of the mission here, the launch mission, we did that with STK Aviator, which is a 6DOF full physics developed flight modeling tool. And depending on when you're watching this, Aviator in version 12.1 has the ability to now model these launch missions to a really high accuracy. So if it's past September 2020, you'll probably have access to STK 12.1, and you can, look into the complex kind of mission that is the launch series here. Reach out to us, call support, email AGI. I'm sure the details are below the video here to take a look at that portion of the mission here. But like I said, we're going to be looking at the rendezvous and proximity portion of the mission here. So right off the bat, you can see that Dragon is offset in its orbit, and it did conduct a maneuver to decrease the velocity in the instance of our launch here in order to at least match circularly the ISS here. And we'll get into the numerical results of the maneuvers as we go through here. But the first thing that the Dragon needs to do is now rendezvous with the ISS before we can complete that docking mission. So if we open up the properties of the Dragon object in STK, again, using Astrogator, we have a set of sequences here in the mission control sequence. We've got kind of 3 or 4 that make up the bulk of the maneuvers that are targeted to the ISS. The first one is going to be a minimum 2-burn delta V rendezvous with the ISS. So the reason why rendezvous and proximity operations are so complex, people spend decades to become experts in this realm. With something like our specific example here, we need to find out how many times we need to maneuver, when we need to maneuver, in what directions we need to maneuver, at what magnitude we need to maneuver, potentially over dozens and dozens of different maneuver sets in order to make this rendezvous and proximity mission a success with the International Space Station. So you have to have a very deep understanding of orbital mechanics and quite a bit of operational experience to design these kinds of missions from scratch. But the reason why I'm highlighting these RPO sequences today for you guys is because our experts back at AGI have basically designed a set of 48 RPO sequences that you can drag and drop into Astrogator now and design whatever RPO mission you want to an extremely high degree of fidelity. They're very robust. They can be finite or impulsive maneuvers, and they can be applied in any orbit regime with full force models. So, and I think I already said this, but they're free, which is just mind-blowing, right? So that's what we have here. And if I open up the add segment selection here and expand the RPO sequences here, you can see some of the examples that you have, right? So you've got forced motion waypoints. That's what we're going to use to actually dock with the ISS today. Kind of a point and shoot sequence. We've got hop, so basically I want to go from point A to point B relative to my reference or target in orbit. We've got hop minimum delta V, just to name a few. Of course, you've got natural motion circumnav, V-bar hop, the list goes on and on. There are 48 of these sequences, all user-friendly. All you have to do is drag and drop in the appropriate order and define the characteristics in terms of spacing relative to your target and whatnot to build a very accurate industry quality RPO mission. Okay, so back to our mission sequence here, and I'll talk a little bit about how these are defined as we go. We've got some basic sequences for the most part here, basically like set reference vehicle. We just want to see, basically we're saying, okay, Dragon capsule, solve for your maneuvers relative to the International Space Station. That's our target in this example. We've also got some coast sequences here. Basically, Astrogator is then going, after a series of maneuvers, it's going to propagate in a high precision orbit propagation force model ephemeris for our vehicle so that we can see what happens after those series of maneuvers are executed. So those are really simple and straightforward sequences. But like I said before, we've got this minimum to burn delta V rendezvous. And if I expand this, we've got 2 propagate segments and 2 maneuver segments. Okay, so that's what's making up kind of the nuts and bolts of this min to burn delta V rendezvous. But if I click on this target sequence, this is why these things become so complicated. You can see that there are over a dozen different differential correctors in this target sequence, which is basically the iterative process in order to figure out those big questions like we talked about earlier. When do I need to maneuver? In what direction? At what magnitude? All throughout our mission. That's what this segment is doing here in the target sequence. This is where the expertise really comes into play. But this is already defined in this sequence for us. And if I go back to the sequence kind of hierarchy here, all we have to do is input our user desirable inputs here. Okay, so I talked about, so with the min to burn delta V rendezvous, we can just say, I want it to occur within this envelope. I need it to occur within 200 minutes in this case. And the delta time is basically our step size. So delta time for search grid in minutes, right? It's looking for a solution with that step size. And I'm not going to go through every single one of these. Every sequence is different, but it basically exposes a set of user inputs most of the time where you want to be after that sequence is complete, and it's going to solve for the maneuvers needed to make that happen. All right, and then the maneuver type here, we've got impulsive or finite. We're going to be doing impulsive today just because this is an example. Hopefully that resonates with everybody. But you can have finite maneuvers throughout your proximity mission, right, which is a big deal. You've also got different engine types that you can use within these different sequences. Okay, so we're using a rendezvous engine. And if I open up the properties of that and go into engine models here, we've got a thrust of 100 newtons for this engine in particular and an ISP of 280 seconds. Okay, and then we've also got a ProxOps engine that we're going to be using once we get closer to the ISS. This has the same ISP but a much smaller thrust of 1 newton. Okay, all of these parameters that we're seeing here are of course open-ended with an STK, and if you are an orbit expert and you are a RPO expert, you can come in here and use these as templates and manipulate them as much as you want. They are not closed sequences or engine models. All of this is user-friendly and can be adjusted accordingly, okay? Okay, so the first thing that we're going to do is rendezvous with the ISS. And if I go back to my 3D graphics window, we are going to rendezvous. I've designated that point to be 10 kilometers offset from the ISS in the radial direction. Okay, so we've got the ISS up here at a higher altitude of 10 kilometers and the Dragon 10 kilometers below it. And we can see that in the data display here, range just over 10,000 meters. And we can also run some reports to see what the range is from the Dragon and the ISS. And again, in this report, it looks like we're about 10 kilometers off. Okay, and the reason why I did this, and by the way, I am not a rendezvous or docking expert here, which just highlights the fact of, as to how usable these sequences are. But the reason I put it offset from the ISS here is because, of course, we're going to have a slightly higher speed being at a lower orbit altitude, which means that over time we're going to kind of start to pass the ISS, pass under it, right? And then the next sequence that we are going to execute on, and by the way, there is a stop relative motion, which means that once you've reached the desired point that you want and you want to maintain that position, you can input a sequence like stop relative motion, and we're going to maintain that offset as best we can. All right, so we're going to then propagate for about just under an hour here. You can see in this coast segment, 3,480 seconds, just under an hour. And then we're going to execute these two different forced motion waypoint sequences to radially decrease that distance to the ISS to a position so that we're about 10 meters offset from the velocity or in-track position of the ISS, and we'll look at all of this in the graphics here. And then we're going to do our last few maneuvers to finally dock with the International Space Station in this last forced motion waypoint sequence. All right, and again, these all have impulsive or finite options. They have the time in which you would like this sequence to be completed in, which is of course going to dictate the magnitude of your maneuvers, and the radial, in-track, and cross-track position that I desire to be relative to our ISS target. Okay, so let's check out what that looks like. Okay, so now we are at a much closer position. We can see here in our data display, we are 67 meters, almost 68 meters from the ISS, so we're getting pretty close. This is after that first forced motion waypoint sequence to execute our rise in the radial direction or ascent towards the ISS. Okay, we also need to start adjusting our attitude of the Dragon capsule so that we are in the proper orientation to conduct the docking sequence, right? So we're going to adjust the attitude of the Dragon capsule here, and you can see that this is happening simultaneously as it raises towards the ISS here. And eventually we're going to be offset in the velocity direction or in-track direction by about 10 meters before we execute that final forced motion waypoint sequence to dock with the ISS. Okay, so it's going to come up to that offset. It's going to halt. We're going to open our nose capsule, and we're going to move in closer to the ISS here. So you can kind of see how it fluctuates up and down here as it maneuvers as best it can to meet this docking position. And lo and behold, we finally dock with the ISS successfully. And that occurs in epic seconds, and this is relative to the 30th of May at about 17,800 seconds. All right, so there you go. We have successfully docked with the ISS. And of course, most importantly, the last thing that we want to do is take a look at the maneuver summary here, right? Because I don't know off the top of my head how many maneuvers that took, what the total fuel usage was, what the total delta V was, but this kind of gives you a glance into how complex this rendezvous and proximity operation mission was, right? So in this maneuver summary here, total maneuvers, if I scroll down, we've got 56 total maneuvers in order to make this mission complete. This is relative to the Dragon. This does not include the stage 1 and 2 launches of the Falcon 9, right? So this is, we've got 56 total maneuvers. In terms of delta V and fuel usage, we've used almost 1,600 meters per second in delta V, and fuel usage almost 500 kilograms. So, quick disclaimer, I have put this together based off of what I thought and looked to be realistic. I have zero experience in rendezvous and proximity operations in the real world, right? I have never designed a docking with the ISS. But I was able to do that with these sequences here, dragging and dropping them in and just kind of playing around with these different desired offsets relative to our target. And then Astrogator has gone and solved all of the complex orbital mechanics in the background, and again, told me when and where these maneuvers need to occur in order to make this mission a success. Of course, if you are an expert, you can use the 48 available RPO sequences available to you to define a much more accurate sequence for this International Space Station docking, which I have no doubt people can do. So thanks for watching, and I hope this is of use to you guys. If you are interested in using these free RPO sequences, just reach out to us and we can get you started.